Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever, and today we are talking about complex numbers. Do you like the complex numbers? I love them. We're going to talk about them right. We're going to say it right, just like the great Nelly Furtado. Don't you make fun. This song is awesome. All right, let's get to it, shall we? Nice little diagram here, Venn diagram of the complex number system. We talked about I already in class, and we'll talk about it a little bit more here in just a second. But if you remember the pattern of the powers of I, they are here, and a nice way to figure out which of the values is depending on the power. Nice little chart. You might want to take a look if you are not down with that. So we know that any number of the form a plus bi, a and b real numbers, and I is equal to the square root of -1. It's called a complex number. And a complex number, well, where did that come from, really? That came from the need to be able to talk about solutions. Let's say you had a solution, particularly in a quadratic, something like square root of -2. Well, with I equal to the square root of -1, we can represent this as root -1 times root 2, right? Which will then equal I root 2. Okay? Purely imaginary if it's only of the form bi. Sum of two squares, we can also write a squared plus b squared as a squared minus b squared times I squared, because I squared is equal to -1. Beautiful, which means we can write a squared plus b squared as a plus bi times a minus bi. That's very handy and stated right here. Here we talk about the real parts and the imaginary parts of a complex number, which are self-evident. Conjugates. Well, you know what a conjugate is. We also have complex conjugates. They are of the form a plus bi and a minus bi. And we represent, if we call one of them z, then its conjugate is z star or z asterisk. And what works out nicely is just like a quadratic equation which has rational coefficients and an irrational root, c plus d root n, then the conjugate c minus d root n is also a root. Same is true with conjugates. If I have c plus di as a complex root, then I know that c minus di is also a complex root, its conjugate. Some nice examples here. Okay? And what follows from this, if I know that these are roots, then I'm able to get a quadratic equation if I know one complex root, or I can get all quadratic equations that have a particular complex number as a root. So take a look at that if need be. It's best if we just do an example, I think. And here we go. Find all real quadratics having 1 minus 2i as a root. Well, what this boils down to is it's going to be in the form of a times x squared minus the sum of the roots times x plus the product of the roots. And that's on the previous page in the orangish box. So if I know that 1 minus 2i is a root, I also know that 1 plus 2i is a root. So all I need to get all real quadratics having 1 minus 2i as a root is to find the sum of these two roots, which is going to be 1 minus 2i, 1 plus 2i, combine those, that gets 2. Product is just going to be c squared plus d squared. C is 1, D is 2 in this form, so that's going to be 1 squared plus 2 squared, which is equal to 5. So the answer would be a times x squared minus the sum, which is 2x, plus the product, which is 5. So any multiple of this will have the complex roots 1 minus 2i and 1 plus 2i. Don't believe me? Give it a try using your good friend, the quadratic equation. Okay, let's take a look at this. Find the exact values for a and b if root 2 plus I is a root of this particular equation, and a and b are elements of the real numbers. So first of all, if root 2 plus I is a root, I also have root 2 minus I as a root. And also, since a and b are real, then we know that the quadratic has real coefficients, obviously. Okay, so we're going to use the same idea as we did right back here, and that is, yeah, this isn't working very well. Right here, x squared minus some x plus product. Okay, so let's just write that real quick. So x squared, come on now, x squared minus some x plus product. So I just need the sum and products again. Works out great, doesn't it? So root 2, so the sum is going to be 2 root 2. Okay. And then the product is going to be root 2 squared plus 1 squared. So root 2 squared plus 1 squared, which is equal to 3. So then this becomes x squared minus 2 root 2x plus 3. But they're asking for the values of a and b here, right? So a, since this is positive generalized, we would have to write this as negative 2 root 2. And then b clearly would be equal to 3. Okay, a little bit more here. If you were to go through, and perform all of these operations, and they're just, giving some specific examples here. It's not a formal proof, but it's showing you how we can get some rules for complex conjugates, and we could do a formal proof, but we'll save that for another time. But here are some nice properties that can become useful. In other words, the conjugate of a conjugate is just the original complex number. And I'm not going to go through all of these, but you can see what's going on there. Okay, so we are going to, what do I have on the last page? Nothing. Okay. Show that for all complex numbers, z1 and z2, and we're going to prove one of them here. z1 plus z2 is equal to, z1 plus z2 star is equal to z1 star plus z2 star. So let's give that a whirl, shall we? Okay, so for A, let's see. Let's say that z1 is equal to a plus bi. And so z2 we will let be c plus di. Okay, so here we go. Z1 plus z2 is going to be equal to a plus c plus b plus di. And so the conjugate of z1 plus z2, or z1 plus z2 star, clearly would be equal to a plus c, the real part, minus b plus di. Okay, so what is that going to be equal to? Well, that equals a plus c minus bi minus di, which can be simplified into, or not simplified, but rearranged as a minus bi plus c minus di, which is the same thing as the conjugate of z1 plus the conjugate of z2. So a very simple proof there, which is what we were after there. Okay. What about b? Okay. Let's make the same assumptions here so we don't have to rewrite them. So then what would z1 multiplied by z2 be equal to? Well, if you work that out, it's no big deal. It's just a plus bi times c plus di, right? Okay, and if we, I'm going to save all the algebra and just give you the final result. That's going to be, and I think it's pretty clear, AC minus BD plus I times AD plus BC. Okay. So then Z1, Z2 star, or the conjugate of the product of those two complex numbers, would be equal to AC minus BD minus I times AD plus BC. Okay. And also, we know that Z1, the conjugate of Z1, times the conjugate of Z2, this is what we're seeing here. That's going to be A minus BI times C minus DI. Okay, so equal there, equal here, and with some algebraic manipulation, that too is going to be AC minus BD minus I times AD plus BC. Okay, and I'm going to call this one equation 1, and I'm going to call this equation 2. Okay, and from these two, from 1 and 2, it's clear I didn't really have to do that. I was just trying to be formal. I guess I could say from 1 and 2, we have a generalization and we have a proof that this, I'm not going to rewrite it, is true. Okay, hope you enjoyed it. I sure did. We'll finish off with some more Nelly Furtado, of course, because we love her. And we'll see you next time. I am out.